Good morning, class. Welcome to our continuations of the lectures on electrodynamics. Our main reference is again Introduction to Electrodynamics by David J. Griffiths, and I recommend you to buy this book because the details of our lectures are found in this book, and most of the materials here are in this lecture are taken from this book. By the way, I could see Eugene, Joven Steve, Adaptar, Michael John Gomez Galliera, Ana Fe Palmero, David Paul Hinayon, Liza May Rodriguez, Marsden Badlisan. So thank you so much for uh, being there on time. So let's review what we have learned in the previous lecture. The vectors, we have studied that, and scalars also. Vectors are quantities with both direction and magnitude. So if you add two vectors, you have to not only manipulate the magnitude, but also the direction. So for example, if you have two vectors, this one connected tail to tail, so if you add them, one vector should be connected to the tail of the other vector. So for example, if you have two vectors, this one, the sum would be, the magnitude of the sum will depend on the angle between them. So if the angle is like greater than 90 degrees, because this is the measurement of the angle, so you have to connect tip to tail. The angle would be, if the angle would be greater than 90 degrees, the magnitude would be small. And then if it's 90 degrees, and if it's less than 90 degrees, it would be large. If it's like 180 degrees, or I mean, if the angle is 0, that's the maximum magnitude that it can have. So it depends on the angle. Um, if you add the vectors, but if you add scalars, you're just adding two quantities in a straight line. So it like 3 plus 4 is always 7 if you do it in ordinary algebra. But in vectors, the magnitude of the sum would be different depending on the angle between them. And the vector addition is commutative here, meaning you can interchange the order. You have a plus b, this is just equal to b plus a. It's also associative, um, meaning that if you have three vectors, if you add three vectors, you can add the first two first, then add the third one. Or you can do adding the second, the third first, and then add it to the first vector. It's the same. For the difference of two vectors, the difference would just be equal to the sum plus the negative of b, meaning the b here has an opposite direction if you add. So if you have an a here and a b here, so your b should be, if you want to get a difference, so it's now different. For scalar multiplication, if you multiply a vector or sum of two vectors by a scalar, a here is a scalar, meaning it has no direction. This a and b have directions. That would just be, you can distribute the scalar. So this is just a times a plus a times b. The a here could be greater than 1. If it's greater than 1, if you multiply the vector with a scalar that is greater than 1, the magnitude will increase depending on the a. But if it's less than 1, the magnitude of the original vector will decrease. But if a is also negative, the direction will also be the opposite of the original. We also had in the previous lecture scalar product, and scalar product is just equal to a dot b. This is just equal to ab cosine theta. AB is the magnitude of a, I mean, A is the magnitude of the vector A here, and B here is the magnitude of the B, vector B. The theta is the angle between uh, the two vectors if they are connected tip to tail. So like this. So the angle will be depends. No? So if the angle is wide, this is the scalar product. If the angle is small, this is the scalar product. So it is also commutative, the scalar product. Here you can interchange the order. So A dot B is just equal to B dot A, and also distributed. So you can have this. It's the same as this, but A here is scalar. But in this case, you have a vector. So you can do this A cross B plus A cross C. Then you can also have vector product of two vectors. A cross B will just be AB sine. So this is the difference between this 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 one is, you have here for the dot product you have cosine, and for the vector product you have sine. And also another difference is this one, the direction. It has a direction n, which is determined by your thumb. So if you cross, for example, A cross B, you have to put your palm first to vector A, and then you curl it to vector B, and then the thumb would be the direction of uh, the vector product. This is the magnitude of the vector product AB sine theta, and n is the direction of that vector, the magnitude and the direction. So for the right-hand rule, you must remember that the direction of the thumb is the direction of the vector product. The cross product, vector product is also called cross product. You can distribute this. So A cross B plus C would just be equal to A cross B plus A cross C. So these are both vectors also. But the vector product is not commutative. It's not commutative, meaning that B cross A is not equal to A cross B, but rather B cross A is equal to negative A cross B, because the direction would be opposite. So if you cross A, for example, your A is here and you cross with the B, the direction would be here. But if it's now B cross A, it's so if this is A cross B, so if this is now B cross A, the direction would be here. So they have to be opposite in direction. So this is negative. For parallel vectors meaning the angle between the two vectors is zero. So this is the angle. If you connect tail to tail, so that is zero. So your dot product with itself, the angle between A and A is zero. So the dot product there is just A square. And for the cross product, that would be equal to zero, a zero vector. This means A square only because the cosine zero is equal to one, and you have A and A here. And for A cross A, you have A and A, but sine of zero is equal to zero, so everything would be zero. And also in Cartesian coordinates, we learned that there are three directions. You have three axes in Cartesian coordinates. Let's look at that here. So you have x in this direction, in that direction, y in this direction. These are perpendicular. X and y are perpendicular. So you have a perpendicular angle here, and then this is y. This is z. This is z direction. This is perpendicular also to y, and z is also perpendicular to x. So they are mutually perpendicular to each other. Z is perpendicular to x, y is perpendicular to z, and x is perpendicular to z. So the angle between those directions or unit vectors is equal to 90. The cosine of 90 is equal to what? The cosine of 90 is what? They're perpendicular. It should be equal to 0. So here, you can write a vector in terms of the unit vectors. The unit vectors is a vector with magnitude equal to 1, and the directions are constant. In Cartesian plane, x hat would always be in this direction. It's constant. So if you get the derivative of a constant, it's always 0. So here it's a constant, it's a constant. For Cartesian coordinates, there are other also coordinate systems which have non-constant non-constant uh, directions. So, but in Cartesian coordinate, you have constant unit vectors. So you can write a vector A in terms of the three components: ax in the x direction, ay in the y direction, az in the z direction. So if you add two vectors, you just add the components of the two vectors. So ax plus bx in the x direction plus ay plus by in the z direction, and az plus bz in the z direction. And if you multiply a scalar to that vector, you just multiply each component by that scalar. A times ax in the x direction plus a times ay in the y direction, az in the z direction. And also, if you dot x with the unit vector x with x, that's just 1. That's just 1 times 1, the magnitude of x vector, unit vector x and unit vector x, that's 1 times 1. Cosine of 90 is also 1. Cosine of 0 is also 1. So you have x dot x equals 1. It's the same thing for y dot y and z dot z. If you're going to get a cross product of x and y, this would be 0 because the angle between them is equal to 90. So cosine of 90 is equal to 0. So everything goes to 0. This is also equal to y cross. It is also equal to y dot x. It's also equal to z dot x, and this is also equal to z dot y. They're 0. If you dot a vector a and a vector b, we showed that in the previous lecture, you will get only ax bx, ax times bx plus ay times by plus az times bz. This is a scalar. There's no direction here. If you get the magnitude of a, which is this one, a cross a, or a dot a, I mean, sorry, a dot a is a square. So this is a dot a. This is also equal to a square. This one. This is equal to this. This is just equal to ax squared taken from here. So if you replace b with a, this is just ax squared plus ay squared and az squared. And if you want to get the magnitude, because this is equal to a squared, you get the square root of that, and the magnitude of this vector is just this one. If you if you know the components of the vectors, then you just square them. If the one of the components is 0, then you only have 2 terms here. So for the cross product, x cross x, what is the angle between x and x? The angle between x and x is 0. And also the angle between y and y is 0, and z, the same as for z and c, is 0. So sine 0 would be 0. So everything will be 0. So for the cross product of 2 unit vectors, I mean the same unit vectors is 0. But for x cross y, that would be z. So let's look at this in the figure of here. You have x cross, so if you have x cross y, that would be z. But y cross x would be negative z. So you just use your right hand and you will, it will help you in uh, erasing your confusion with the direction of the cross product. So x cross x, y cross y, and z cross z would just be 0, and x cross y would just be z, but this is negative of y cross x because the direction is different. Y cross z is just equal to negative z cross y is equal to x. So look, x, y, z, and this is y, z, x. There's an order here. X, y, z, y, z, x, and then z, x, y. So if you cross z with x, that's just equal to y. So just use your right hand to be able to know the direction. So in this lecture, we always use the right hand coordinate system, right-handed coordinate system. So if you want to get the cross product between one vector to another, you can write in this way. This is the three components of the first vector, and this is also the three components of the second vector. So if you do distribution, you do expanded multiplication of these quantities, you will get only, because like for example, ax x hat cross bx x hat, that would be 0 because x hat cross x hat is equal to 0. So everything, all the zeros will cancel, and then you'll be left with only 6 terms. All the other 3 terms would go to 0. And so your cross product would just be equal to this. But you can write it in matrix form, in a determinant form of the matrix. You have A cross B. You can write this in this kind of matrix. You have the first row, X, Y, Z, which are the unit vectors. And then the second row will be your components in the of the A, the vector A here, the first. If this is B cross A, then B should be here. But this is A cross B, so you have to write A here, and then your B here. So it depends on the order of uh, the vectors you're crossing. So this is Bx, By, and Bz. And then you have X here. You know how to get the determinant of a 3 by 3 matrix. So you can write X here, and then from this X you can cover this one and cover this one. So you have AYBZ, the product minus AZBY. AYBZ minus AZBY. For um, Y here, you can cover this column and cover this column. Then you have AXBZ minus AZBX. This for this direction here, you have AXBY minus AYBX. So that's how you get the determinant of a 3 by 3 matrix. So that's just a review of your algebra. Now we'll go to an example. Here you have consider a cube of side 1. You have side 1 cube here. All of the sides are of unit 1. So um, you will find the angle between the face diagonals of a cube. The face diagonal is this one. It's lying on the face of a cube, and then the other diagonal would be uh, here. So there is an angle between A and B. They're connected. They're connected tail to tail. So A, the vector A here, would have what coordinate? Because the corners of this cube would be here 1 0 0. This is zeros. What is the coordinate here? The coordinate here would be 0 0 1. So the coordinate here would be what? 1 0 1. No, this is 1, and the 1 for x, for y it is 0, and for z it is 1. Because the y would just be here and it's 0 here. So 1 for x, 0 for y, and 1 for z. So this is 0. Oh, this is 1 0 1. For b, you have x, of course, here is 0, and y is equal to 1, and z is also equal to 1. So your b will have 0x, 1y, and 1z. So these are your diagonals, the vectors in the diagonals. So if you want to get the dot product using this formula, using this one, then you just multiply the respective components. So this is 1 dot 0, this is 0 dot 1 dot 1, and 1 dot 1. So A cross B would just be equal to 1. So this is 1. This no, I cannot go here. 0 is here, and this one is 0, and then your 1 would be this one, and then your 1 here would be that also. So your A dot B is equal to 1. In abstract form, you have A dot B equal to AB cosine theta, right? But what is the magnitude? What is the magnitude of A? What is the magnitude of A? The magnitude of A, you can use this formula. You can use that formula. So what is the magnitude of A? This is 1 square plus 0 square plus 1 square is equal to 2. And you get the square root of that. This is the magnitude of A. And for B, you have 0 square plus 1 square plus 1 square. So you have 2, and then you get the square root as the magnitude of that, and then you will have square root of 2. And cosine theta is just what you're going to find. This is the angle. Then this one, AB, which is 1, is equal to this is equal to that 1. So 2 cosine theta, square root of 2 times square root of 2 is 2. This is equal to 1. So 2 cosine theta is equal to 1. So what is cosine theta? Cosine theta would be 1/2. And then the arctan of theta, arctan of cosine theta, or inverse of cosine theta equals 1/2 is just equal to 60 degrees. And you know this in your algebra, or in your trigonometry. Also, you can get the angle by completing the triangle here. This triangle, this diagonal is just the same length as this diagonal. You can also draw a diagonal here, and you form an equilateral triangle. or an equiangular triangle. An equilateral triangle is also an equiangular triangle. So you have the same angle here, and the angle between and the sum of the angles between the sum of the angles of a triangle, the interior angles of a triangle is always 180. So if you have 60 here, 60, everything would be 60 because they're equiangular triangle. Equilateral meaning equal sides, equiangular means equal angles. Now we go to the triple products. We're now finished with the example. So the angle between A and B is equal to 60. And then we now go to the triple products. So the cross product of two vectors is a vector. The cross product of two vectors is a vector. So therefore you can add, you can dot it or you can cross it with another vector. So the first of the triple product is called the scalar triple product. And this is represented by the symbol A dot B cross C. Why can we do this? Because B cross C, this is a vector, and then you're dotting it with a vector. So that's why it's valid. So geometrically, A dot B cross C is the volume of the parallelepiped generated by A, B, and C. The BC is the area of the base, the area of the base. Areas of base. And A cosine theta is the altitude. A cosine theta is the altitude. This is the altitude. So that's the volume of the parallelepiped. A dot B, A dot B cross C. So you can get the parallelepiped by projecting the vectors. So for example, A, you have A here, you can project it here, you can project it here. It's the same vector. You can project that here. And then for B, you can project this here, you can project it here, you can project it here. You can project it here, you can project it here. And then the C, you can project this C to here, here, and here. So that's the parallelepiped or parallelepiped if you're having difficulty in pronouncing it. Parallelepiped or parallelepiped. So A dot B cross C is also equal to B dot C cross A, and this is also equal to C dot A cross B. Look at the cycle of the alphabet. A, B, C is also A, B, C. This is also A, B, C. So this is like an alphabetical order. Also here, these are also equal. A dot C cross B. This one is not. This one are not equal. This one they are not equal, but the magnitude is the same. They are not equal because the directions are opposite, but the magnitudes. There's no. I'm sorry. There's no direction here. This one is negative of the other. This one is negative of this one, or this one is negative of that one. But sorry, there's no direction here. This is purely a scalar, no direction for this triple product. But this vector here, that's why it becomes negative because it's reversed here. This one is also equal to this. So this is what you call the alphabetical order, and this one is not the non-alphabetical order. In component form, which is similar to this, what you saw before, this is cross product of two vectors. Here is the triple product, scalar triple product of three I mean, scalar triple product of vectors A dot B cross C. So the first row here would be the components of A, and then the second row would be the components of B, and then the third row would be the components of C. And so you get the same as this AX here. You have, in this case, you have AX. In this case, this is BX and this is CX. So you can just replace AX and then everything just follows. You get the magnitude. Note here that you can interchange the cross product with you can interchange the cross product with the dot. So you can place the cross product here with the dot. So but the parenthesis would be here, not here. Uh, uh, if you retain the parenthesis, that would mean nothing. So this one also is the same as this. So if this is also that one, and then this is also this one, and this is also this one. So that's the same. So here is a meaningless expression y. A dot B is a scalar. There's no direction, only magnitude. And you're crossing with it with a C, which is a vector. So a scalar cross a vector is not possible. You can only cross a vector with a vector. In this case, you have a scalar, it's not possible. So this is meaningless. Then we go to another triple product called the vector triple product. And this is represented by this expression. A, this is a vector, magnitude and direction, of course, is required. And then you have B cross C, which is also a vector. So this one is a valid expression. It's a valid quantity. So you have a vector crossing a vector. This can be simplified through Baka-Bull. The Baka-Bull. Meaning, this is the meaning of the actual meaning, mathematical meaning of the Baka-Bull. So if you have A cross B cross C, this is equal to B times, there's no symbol here, just multiplication, A dot C. This one is a scalar. You can multiply a scalar to a vector, minus C, A dot B, also a scalar, multiplied to a vector. So this is now your Baka-Bull. So here you have an entirely different vector. Why? Because the vector triple product is not associative. So this one here is A cross B. This is different from here. These are not equal. So if you interchange the order, you have negative C cross A cross negative C cross A cross B. And by the Baka rule, this is equal to this. So they are not equal. This one is not equal to these are not equal because they are not equal. By the way, these are, you can write this, you can, these are equal, by the way, because of the, I mean here, this one is equal to this because of this. You can associate it, the um, the dot product is commutative, no? So you can interchange this with C. So this is, you can write A cross B dot C, A cross B dot C. So that's why they're equal, because that is this one, and then this one is just this one is just equal to that one. That's for the scalar triple product. Remember, scalar triple product, and then you have the vector triple product. You have to remember the expression. So this one you can simplify by using Baka rule. So if you have this expression, you can simplify it. Uh, by this, and also if you have this kind, you can simplify it. You can simplify it by this expression. Just use this this expression, this identity. I mean, so later on, you can prove all of this by. I'm not going to prove these identities here, but you can prove this yourself by doing by uh, letting all the vectors be written in component forms. Then everything would be easy to prove. So we don't intend to prove all of these identities here, but uh, by yourself you can do it with the examples also being shown in this lecture. And then in solving electrodynamics problem, in solving electrodynamics problem, we'll be dealing with position, we will be dealing with displacement, and we'll be dealing with separation vectors. That's the difference between two vectors. So position, displacement, separation vectors. We will explore that here. So a point in three-dimensional Cartesian plane. So if you have a point here, that point would have coordinates of x, y, z. That x, y, z will be the components of that of the vector um, coming from the origin to the point. So this is the vector coming from the origin to the point. So if the point here is x, y, z, then there is a vector uh, representing the direction coming from the direction of magnitude coming from the origin, which is 0, 0, 0. The origin would be 0, 0, 0 to the point x, y, z. So this is the position vector. And the x here would just be the x component, the y would just be the y component, and the z would just be the z component. And the direction is x hat, y hat respectively, as well as the z hat. So this is the position R. And it has a component x, because in three dimension, so if you draw it like this, this is the y, this is the x, this is the y, this is the y, and of course this is the z. No? So anyway, just so this is now x, y, z, the components of the position vector. What is the magnitude of this position vector? So we have this expression, and then the magnitude will just be x squared plus y squared plus z squared, the square of that. And then if you want to get the unit vector, there is a unit vector here. That's the unit vector has a magnitude of 1. but retains the direction of the vector. So this is how you get the unit vector pointing radially outward. So here I will have to wait wait for some seconds. So this is the unit vector associated with r. This has the same direction as r, but the magnitude is 1. Now, if you want, so from this point, so if from this point you want to move a little bit, like you want to move one step or a very small step called dr or dl, for example. You want to move a very small step from this point to some point, to some other point, but very small, infinitesimal. Infinitesimal meaning very, very small. So there will be a change. There will be a change in the displacement vector because you're now going from xyz to x plus dx, y plus dy, and z plus dc. So you're changing the position. There is an infinitesimal displacement there, and then the infinitesimal displacement represented by this. It has 3 directions, x, y, and z. But since you move from since you move to another point, then there is a change in the x component, y component, and the z component. And the change would just also be infinitesimal because you only move very small step, infinitesimal. So this would also be infinitesimal. This one is also infinitesimal, and this one is also infinitesimal. So in other problems, we will be dealing with a source point, and a field point. I told you about 2 charges in the first lecture. So one of the charge would be producing field. I mean, both charges would be producing field. So here is a charge that would be producing a field. The other charge will be detecting that field, and the other charge will be located in another point. So there's what you call a source point. A source point is the point where the field is coming from. And the field point is the point where you are measuring the field. So you have a source point and a field point. So usually we denote a source point with the vector r. So this is the position in the Cartesian coordinates. And the field point would be denoted by vector r. This one is r prime, sorry, r prime for the source, and then just pure r for the field point. There is an angle between them. So if they have the different angle, I mean, if there's a difference of the angle between them, then there must be a difference between the two vectors. This is the difference between the two vectors. This is r prime minus r. Or sorry, this is control Z. This is r minus r prime. This because r prime would be negative r prime would be here, and then your scripted r would be here. So this is r minus r prime. This is r minus r prime. Okay, that vector. This is called the um, difference or the separation vector between point the separation vector between point R. This is point R, x, y, z, and this is the R point R prime, which is x prime, y prime, and z prime. But the vector for here is x x hat, y y hat, z z hat, and the vector for here is x prime x hat, y prime y hat, and z prime z hat. So that's the separation vector, which is represented by this r minus r prime, and the magnitude is this. So how do you get the magnitude? It's just what, the difference. So later, so this is the magnitude. You can get the modulus of this, and then the unit vector is also calculated by that formula. So R, the scripted R, the separation between R and R prime is just this one in component form. So you have, this is R minus R prime, so this is just X minus X prime, Y minus Y prime, and Z minus Z prime. So X hat is the direction, Y hat is the unit vector directions of the of the difference in the components. And then if you want to get the magnitude, this is just the formula, that one, and then the unit vector would just be this one. So it's quite easy. So now, by the way, if I ask you, um, what what does an apple look like in your, or what does a mango look like in your house? And if you ride on a plane, the mango would still look like a mango. So if you're in your house, you're dealing with one coordinate frame. And if you go to the airplane, as it takes off, you're dealing with another coordinate frame. You're convenient with another coordinate frame. But the mango does not change. The mango in your home or in your house would be the same mango in the plane. Because the mango is not a vector, it doesn't transform. However, the vectors, when you change coordinate frames, it will transform. The components would be different. So a vector is a quantity with magnitude and direction, and it transforms with a change in coordinates, or with a change in the coordinate frame. So there's a transformation law for vectors, for converting vectors to another, to finding components of the same vector in another frame. So for example, you have this, the direction of the x-axis here would be going to you, out of the page. So x-axis would be just a point here going to you. So this is y and z. Suppose that you rotate the x-axis. You rotate the x-axis. That's why you're now having a new z, which is z bar, and then a new y, which is y bar. So you rotate you rotate the x-axis, and then this one forms an angle difference between z and z bar, which is the same angle as the y and y bar. So these are the same angle. So there is now, so the original component of a on the y-axis is a cosine theta. This is the original component. This is the original component of a, which is ay. The new component of a on the y bar axis is this one. This is the new component of A on the Y bar, but this is the component of A in Y axis. So as you can see, the magnitude or the length of the arrow are different. So the magnitude is different for the components on the Y. And for the Z, the original component would be AZ, but AZ here would be here only. So there is a new component. The original component would be AY, A cosine theta, and AZ would be A sine theta. But the new one, AY bar, would be A cosine theta bar. Theta bar here is the difference between theta minus the angle phi, the rotation angle. So the angle phi, this is A cosine theta. If you expand this by some trigonometric identity, you will get this. And then, but A, A cosine theta, this one would just be AY. So this is AY cosine phi, and then A sine theta would just be AZ. So you will have sine phi times AZ. So your AY, so your AY is now, our AY bar is now equal to this in terms of the angle phi, the rotation angle, the the rotation when it transforms. For AZ, you have this expression because it's a sine theta bar, and theta bar would just be um, theta minus phi. And then if you expand that, you will get this expression. So you can write this in matrix form. In your algebra, you have done this. So AY bar would just be equal to, if you multiply this column to this row, this column, so AY times cosine phi and AZ times sine phi, that this would just be this one. And this one, AY negative sine phi and AZ cosine phi. So that would be that one. In general, for 3 dimensions, um, you will have this matrix. So in this case, X here, in this case, your AX bar, because you're only rotating on the x-axis, your AX bar is just equal to X. So that means this one, for 3 dimension, this is just equal to 1, because AX times RXX should be equal to AX bar. This one would be 0. This is 0. This is 0. Control Z. This is 1. This is 1. This is 1. This is 0. This is 0. And this is also 0. This is also 0. Because AX times RYX should be 0 here. And AY times RRY should be equal to cosine. This one is equal to cosine phi. And this one is equal to sine phi. This one is also equal to negative sine phi. And this one is also equal to cosine phi. So here is the 2-dimensional or 2x2 matrix equivalent to this. This is the general form. So compactly, you can write this expression in terms of the summation. So you can write this. You can write this matrix as this, and AX AY would just be this one, and then um, Rij would just be this. J would be coming from 1 to 3, or this is XYZ. This 1, 2, 3, or XYZ. AJ would be representing this. So in this case, if you want to find A2 bar, this would just be equal to this is 2, so this is 2. Then you add all the three components. So R21 A1 plus R22 A2 plus R23 A3. Or if you want to retain the XYZ labeling, so if you want to find AZ bar, this is just equal to RZXAX plus RZYAY um, RZZAZ. So that's just what it means. You are summing the J here, 1, 2, 3. So you are summing 1, 2, 3. There are X, Y, and Z, and then the I here would be the component you're looking for. So for example, this is 2. This would just be 2. This would just be 2, and this also should be 2. But the J you have to sum 1, 2, and 3. So for the elements of R in the rotation about the x-axis here, as I've said, Rxx is equal to 1, Rxy is equal to Ryx equal to 0, and then Rxz equals Rzx equal to 0 here. So that's for, so if you want to transform um, a vector to another coordinate frame, you should be able to find um, this matrix. Should be able to find this matrix. So in this case, this matrix is a reduced 2 by 2 equivalent of this matrix. So for example, if that is just in the rotation of AX. But this matrix also will have another form, no? In another coordinate system, Rx would have a value, Rxy would have a value, and all the elements here would have a different value. So if you're transforming a vector with that specific matrix, then you can use that matrix consistently to get uh, the transformation of that vector in another frame. So because if you go to other parts of the universe, the transformation is different. So you have to use that transformation consistently in order to get the transformation of this vector. This is a very simple vector. This is a vector, a transformation of a three-component vector. But if you have more components, then the matrix would have more elements. So formally, a vector is any set of three components that transforms in the same manner as a displacement when the coordinates are changed. So you can transform a vector, but later we will show, especially in the curvilinear coordinate system, we will show how these transformations are used. So talking about matrices, there is what you call tensors. A tensor, for example, is like a second rank tensor is a quantity with 9 components. And the components are this one. And for example, Txx can be written like this. Compactly, you can write it like this. But for now, don't worry about this. If you don't understand this, then it's fine. For as long as you know how this works. For now, we will work this later on, maybe in the next semester. And then if you have an nth rank tensor, it has n indices. So for here you have, this is a second rank tensor, so you have two indices only. For nth rank tensor, you have n indices and then three n components. And this transforms with n factors of r. So this is only rank 2, so you have only 2r. But if you have n rank tensor, then this would be n r's. And by the way, a vector is a tensor of rank 1. Rank 1 because look at the transformation. This is only 1r. That's rank 1 for for vector. For a scalar, the tensor has rank 0. So that's the difference between a scalar and a vector. So we will be studying about differential calculus in the next lecture, which is on Thursday. So I hope all of you will be able to attend the class, because right now there are only few people who are um, joining the class. I don't know if they are busy or they don't have internet connection, but I hope more of you would be able to attend the class and interact with me in our Google Classroom or in our Molly Classroom. I will be posting the link of this lecture in order for you to review it. And the slides, I'll be giving this when everything is finished, when all the chapter is finished. So interact with me, because by your interaction I can also evaluate you, and the evaluation, your grade will be based on the evaluation that I have. And then also some problems would have to be solved by you, but I will give the problems later once we have consumed most of we have presented, I have presented all most of the contents of this chapter. So please interact with me in the forum. Interact specifically uh, on this chapter, on the lecture, because that's very important. That I know that you are, if you're learning something or you're confused on some parts of the lecture. So thank you so much. Thank you for your time, and see you next meeting. That will be on Thursday. Thank you. By the way, some people are also here, but a little late. Era Belieno, Ana Fe Palmero, Jay Dulog, Jezreel Daigam, Grace Dave Tosino, Arya Nicola Libas, and then you have GJ also. I don't know the full name of GJ, so you can also write me with your. You can write in the comment your full name. So that's it for now. See you on the next meeting.